it's a diagram. Okay, it's a diagram for us to easily identify the factors. Okay, so I think we can do it now. Yeah. Okay. Okay, means this one is for us some criteria. Okay, some criterion for us to identify number of factors here from the output. Okay, so we see now. Yeah. Where? Oh, okay. Thank you. Thank you. I see first. Oh, okay. Yeah, it's recording. Okay, it's recording. Yeah. Okay. Okay, it's recording. Yeah. Okay. Okay. So we continue. Oh, okay. Yeah. Thank you. Thank you. Okay. So. Okay. Okay. So now we see the same data set. We do data analysis. Now, I mean data analysis for the factor analysis. Okay. So we use the same data set now. Yeah. Okay. Okay. I think it should be this one. It's correct. Okay, this one correct. Okay. So, why yeah? Oh, okay, got. Okay. So, okay. Maybe give it 10 seconds. Yeah. Make sure you have the data. Okay. So now we see the wait. Okay. Here already full. Okay. Wong Mei Si, hello, Wong Mei Si, I think your name appeared 2 times, is it? I think I already marked for you. It's okay, I mark again, don't worry. Why Why your name appear 2 times? Okay. You check email to admin later. Yeah. Okay. Only once. Oh, your name only in ODL. How about the second? Okay, quickly. Yes, correct, 2 times. Okay, in ODL, also in PT20. Okay, email to the admin. See how. Okay, why we got 2. Okay. Okay, so now we see the filter analysis using the same data set like what we used in the yesterday class. Okay, so we go to analyze, dimension deduction, and then filter. Okay. Okay, so after that, what we do, we run everything, all the metric variable, yeah, but except the 3 variables, yeah, except 6. Okay, 6. Okay, unselect, just use a control. The control X6. Therefore, we unselect X6. Okay. Also unselect 13 and then 15. Okay, the rest we run. We only do one this 3. Okay. 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 So yeah, one more thing, you don't click OK too fast, okay? Because I need to do a lot of things here, okay? So therefore, we use the one output, to discuss the rest of the slides, okay? Hopefully, hopefully can finish this chapter today, okay? So we see, okay. Now we see, okay, move all the variables here except 6, 13, 15. Yeah, we tested yesterday that we should not include these three in the data analysis. Okay. Okay. If no problem, descriptive, we still can see the entity image, which is correlation, and then KMO. Okay, KMO. Okay, so we click OK. Continue. Click continue. Okay. Extraction. So here we use principal component. Okay. Yeah. Here you tick here. Script plot. It means we want to see the diagram. Yeah. Okay. The diagram also, you have this diagram, similar diagram in your next slide. Okay. Okay. So now we do the data driven. Therefore, extract using the eigenvalue, more than one. It means any component with the eigenvalue more than one means we want it. Okay. So yeah. One is the quite standard, okay, standard value. Okay, just use one. Okay. Okay, if no problem, click continue. Yeah. Okay, if no question, no. Okay, so if no question, now we click rotation. Yeah. So remember, rotation is the method to help us to find better, for us to do the grouping better. For us to easily identify the factor. Okay. Okay. So, of course, you see this later one by one. Don't worry. Okay. But now we use this one, this process, this procedure to get all the output that we are going to use. Okay. Okay. So now you take this one first. Okay. You take this one first. Direct or beaming. Yeah. Okay. This one is for uncorrelated. Sorry, correlated. This is for correlated. Okay. Okay, and then continue. Yeah. Okay. This one also going to use. Yeah. Scores. You tick here. Save as score. Okay. Limited regression. Okay. So this will be the means they're going to create a new column for us. Yeah, they call it factor score. Okay. Of course, how to use it we discuss in a short while. Now we get all the important output for us first. Okay. Okay, and then continue. Yeah. Options, I think nothing. Nothing. Okay, it's okay. Yeah. Okay. Any question you want to ask? Okay. Quick review, descript, KMO, entity image. Okay. Extraction, script plot. Okay. The rest just follow the default. Yeah. Rotation, we use the obimin, direct obimin, which is the correlated. Yeah. Okay. Score, tick. Yeah, tick save as a variable. Means factor score will be a variable. Okay. So we see this. This all. We click OK. Yeah. Wait for 10 seconds to get the output. Yeah. Okay. So we see a quick review on what we discussed. It's okay. Another 5 seconds for you. Yeah. Okay. Make sure you get the output also. Yeah. Okay. So now, quick review on the requirement. Remember, KMO must be more than 0.5. Here is already more than that. Therefore, the overall they means they have certain degree of coordinarity. Yeah, the MSA is quite good. Okay, so more than 0.5. Yeah, for the KMO statistics. Okay, and then this significant is for the balance test. Okay, also quite good because it's significant. So means you can reject the null hypothesis. Okay. In the image, we see the second one, the anti-image correlation. Yeah. So all above, I mean the general value all above 0.5. Therefore, it's good. So means that the individual variable also should include in the factor analysis. Yeah. Okay. So because we already excluded the three variable, that is not that important. Yeah, for us. Okay. Okay. So if no problem, now we see the eigenvalue now. Yeah. Okay. So this actually also discuss a little bit, means we should extract four variables. Yeah, you see this column total. Yeah, all the values here above 0.1, above one. Yeah, so we take 1 until 4. The rest not important. Okay, so means we extracted four factors. Yeah, from here. Okay. Okay, so if no problem, now we see the scree plot. Actually, the scree plot is also linked to the eigenvalue. You see the first component 4.7, about 4.8. Okay, you see the scree plot, the first component here, 1 here. On the x-axis, 1 means is the component 1. The eigenvalue is 4.8. Can you see?
So the component 1 is actually a combination of variety.
Yes, correct. Correct.
Right.
Correct.
But we never know where the system generate the 4.791, right?
Okay.
Or we can sum based on the above.
Okay. Good question. Yeah. So how they compute 4.79? Actually, 4.79. Yeah. It is sum of square. Yeah. Okay. We can do. Okay. We can do it now. Yeah. Okay. So. Okay. So we can do it now. Yeah. So how they compute 4.79? Is it your question?
Yeah.
Okay. We see this now.
Component 1.
Okay, yeah. Okay, good question. Okay, we see this now. Yeah. So actually, sum of square. Okay, sum of square from the matrix. Okay, from the matrix. Okay. 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 Now it's very good. I no need to key in. Yeah. So already here. So you see, C8. Okay, until C8 until C19. Okay. So what we do, we define the. Of course, the software computed for us. Okay, but you want to know also no problem. We do this power 2. Okay. Any question? Yes. So means 1 here means component 1. Okay. Column C is component 1. And then column B actually list of the variable that we have. Yeah, from the data set, from the SPSS data. Okay, just now. Okay. So 0.363 means it's the relationship between x5 and component 1. Component 1 is also the factor 1. You can call it factor 1. Only the name different, but it's a factor 1. Okay. So we get this is the square. Yeah, this is how they do the calculation. Okay. So we square it for all until here. Okay. Okay. If no problem, now we see the total from H8 until H19. Okay. Sum. Yeah. H8 until H19. Okay. 4.791. Can you see? Yeah. Okay. So this is how they compute this. Okay. Yeah. Okay. Okay. So if no problem, now we come back here. So therefore, the script plot, okay, yeah. Therefore, all they link together. So we see second component here, yeah. And then the eigenvalue is 2 by something, maybe 2 by 3, about that, about 2 by 2 or 2 by 3. So yeah, about here, it's same thing, yeah. So 2 by 2, 3, 4. Okay. So you see the cutoff point is here 1. Yeah, therefore the rest all below below 1. Okay, means we only take the first 4 components, means the first 4 factors. Okay, means these 4 factors they link together. Yeah, okay, they link together and have higher relationship. Okay, higher correlation. Okay. Okay, so okay, so if no problem, now we see. Yeah, okay. So actually done already. This part, yeah. Okay, we see next, yeah. Okay, so we see the slide again. Yeah, so therefore we done already for this part, and then also the script plot. Okay, so as I mentioned just now, the latent root actually is also eigenvalue. Can you see here? Yeah. So it's eigenvalue criterion. Yeah. So they put here. I mean for this here there is of course data different. Yeah. Therefore they keep 8. Yeah. They have 8 components. Can you see? Yeah. So until here. So okay. So component number 8 also consider. Yeah. Therefore until here. Okay. Okay. So if no question, now we see next. Okay. Okay. Now we see a bit more on choosing both component and common factor analysis model. Yeah, you'll get similar result in the common research setting. Yeah. So 30 or more variables, yeah, or commonality of 0.6 for most variables. Okay. We see this one now. Okay, this one. Yeah. Okay. Commonality. Now we see this now. Okay. Okay. Wait. Before this, you can see, okay, I discussed already, yeah, the impact of the eigenvalue, meaning that if higher means they have higher correlation, yeah. Let's say eigenvalue high, meaning that in that factor is very important, yeah. Okay, it's the maybe it's the first important, it's the most important factor, okay, because the eigenvalue is quite high, okay. Now you see the commodity, okay. We still can use the same output. Yeah, okay, here. Okay. Okay. Now what I do, I want to compute. Now I only want to see these 4 numbers. These 4. Okay. So what I do, I find each number here, I take power 2. Okay, okay, okay. I know why already. Okay. So each number here, I take power 2. Okay. And then also this number, power 2. Okay. The third number also power 2. Okay. One more. Yeah, like this. Of course, the software computed for us. Okay, yeah. But so far, any question? Because now I want to compute. I want to show you how the software compute this value, commonalities. Okay.
Sir, I'm not sure whether I can ask this.
It's okay, yes. Yeah.
How I mean, the component matrix is just now the 0.363, all this information.
Wait. 0.6, 0. Are you saying this one?
Yeah. These
Okay.
are what we call the loading, right? I mean, the relationship between the variable to the factor, right?
Yes, correct.
But the factor again is a group of the variables. So in fact, it's like a relationship, what I call a correlation between is one component to is the whole group, right?
It's correct. You can say like that. It's correct. One component to the whole group is correct.
But again, I don't know why, because component 2, 3, 4, all they also have all the variables. So I'm not sure how they can arrive at each different values for each component. How they choose? I mean, some are higher, some are lower.
Okay. Good question. Good question. Okay. So I mean the factors that they closely link together. Okay. Therefore, that will be the common higher relationship among them. So therefore, higher common variance, higher relationship. Okay. So okay. I try to give you very good question. Okay, very good question. But of course, it's a little bit technical, but I try to give you some idea on this. Yeah. Okay.
Yeah, thank you.
Yeah. No, cannot be randomly. They're based on formula. Okay, they're based on formula. It's not calculated randomly. Okay, so they're based on the common variance. Yeah. Okay. Let's say I think I given you the similar example. Is it similar? Okay. Uh, okay, it's okay. Yeah. So let's say like this. Yeah. This is the Likert scale 4, 5. Yeah, 1 until 5. Okay. So x1, x2 are two different variables. Okay. But let's say like this. Yeah. Okay. Okay. So okay. Yeah, like this. Yeah. Therefore, x1 and x2 they suppose group together because they have quite similar pattern. Meaning that the here one is the respondent one. Okay. ID, yeah, ID. Yeah. So respondent 1, 2, 3, 4. Yeah. Okay. You see the pattern? Respondent 1, all the respondent, all 6 respondent, they all tend to answer 4 and 5 in general. Okay, this is the pattern. Okay. So let's say 3, the 3 is the x3 is the variable. Okay, that is, yeah. Okay. So x3, when the system, when the survey compare x2, x3, they find that not much relationship. Okay, but x1, x2, yes, quite high relationship. Therefore, the group x1, x2 together.
So that means also x1, x2, their variance is almost the same, right? Also,
Again,
their variance
variance
variance is
uh, you can say like that because they have a more common variance. Means common variance means their similarity. They are more similar among these two. X1, X2 quite similar. X2, X3 different a lot like that.
okay. So the idea is the component one is they find the most of variables that can have a common variance. Then the component 2 is the second most.
Yes, correct.
Then but they have to test all variables of each
Ah,
component relationship to its own factor.
yes, correct. Okay, very good. You already understand.
Okay.
Okay, thank you. Okay, so now we come back to the here. Okay, so means now what I do, I want to compute the this one. Is correct. Okay, compute the commonality. So we take square, but now we focus on each row. Now we see x5 first. Okay, of course I only see x5. Okay, so the rest you can use it. You can compute it if you want using the same method. Okay, so each one you take power 2, and then you sum up these 4 numbers. Okay, yeah. Okay, so you get this 0.759. Okay, 0.759. This is for the what? For the x5. Okay, and then we see x5 from here. Can you see x5 0.759? Yeah, commonalities 0.759. Yeah, don't worry. Any question on the calculation? I will tell you the meaning. What is important? Okay. If no problem on the calculation, we see the meaning now. Okay. So the meaning is that of course higher means more important. Yeah. But what kind of importance? Okay, we see. Okay. Meaning that this variable they contribute 75.9%. Yeah. To these four factors. Okay. Let's say you include one more. Okay. Therefore here maybe they have another few values like that maybe. Therefore the percentage will increase. But here 759 means about 75.9%. Okay. 75.9%. They contribute 75%, 75.9% of the variation of this variable contributed to the four factors. Can I see? Yeah. Therefore, lower means not too important. Higher means important. Okay. Therefore, you see, we also know that this variable they contribute more to the factor 2. Means e-commerce and also factor 2 have higher relationship, but not much on the third factor. Okay. You think this way, the idea is quite similar with R square. It's quite similar with R square. Okay. They can explain 75.9%. You can explain this way also. It's correct. Okay. Therefore, higher is important. Higher is means important. Lower means not too good. Okay. Any question on this this part? Commonalities. Yeah.
So yesterday you were saying that some variables can be overlapping with in other factors.
It's correct. You are right. Overlapping. Good question. Thank you. Okay. So overlapping still possible. In this table. In this table still possible. Example. You see the wait, yeah. Okay. In general, you can put 0.6 and above. 0.6 above considered important. Example, x5. x5 should belong to a factor 2 because 0.75 here, but the rest is small. Okay, but sometimes overlapping. Okay, example
X9 or X10.
Wait. Oh, okay. Here don't have a good example, but let's say we use 0.5. Okay, then got example. Okay, let's say 0.5. Okay, so therefore x9 overlapping means you don't know x9 belongs to which factor. Can be 1, can be 2. Because 0.656 and then negative 0.532. Therefore, you don't know x9 belongs to which factor. This is an example of overlapping. You call this cross-loading. Cross-loading. Okay, no problem. I type it. Okay. Okay. So in statistics, we call this cross-loading. Okay. Of course, in the normal language, you say overlapping. Yeah, it's cross-loading. Okay, it means you don't know the variable should belongs to each factor. Okay.
When we are not sure, then we just put it into two factors.
Okay, good question. Thank you. Yeah. So this is what we are going to discuss later in the rotation. Rotation can help us. They make our life easy. Okay. This one later. Not yet this the part yet. Yeah. Okay. Okay. So any question so far? Okay. So if no, now we see next. Yeah. Okay. Okay. So therefore here, so we need 30 or more variables. And then community should be 0.6 for most variables. Now you can see this. Again, the output 0.6 and above. Yeah. Okay. So therefore, yeah, you want this. Means therefore, if you want, you can drop x8. Can you see? It's quite small, 0.492. Because we already filter 3 variables. Therefore, now this one is considered quite good already. Only one variable with the commonality below 0.6. Only one. Means if you want, you can also drop this and do again. I mean, your capstone maybe yes, but not for the assignment. Okay, assignment we don't need to meet so high standard in the assignment. Capstone, yeah, is important. Okay, so 0.492 below 0.6, therefore not too good. Okay, so okay. So, but based on here, still consider belongs to factor 2. Still not too good. Still not too bad. Okay, let's say we keep it first. Okay, so if no question, now we continue. Yeah. Okay. So now we see the slide. We are here. Yeah. Okay. So therefore, this is PCA. PCA is the most appropriate when data reduction is paramount. But again, different, not too much actually. Yeah. Okay. So, but common factor model is best in your specified theoretical application. Yeah, yeah, theory support, therefore use the factor analysis. Okay. So, any decision on the number of factor to be retained should be based on the these few consideration. Okay, we see one by one. Okay. Use of several stopping criteria to determine the initial number of factors to retain. Use a few criteria. We see the first one is the eigenvalue. Yeah, more than one. Okay, discussed already. Okay. This one also discussed in the last class. A predetermined number of factors based on research objective. Yeah, means you find that in your capstone or thesis, you supposed to have 6 factors, 6. Okay, therefore, from here, you resign, you prepare the questionnaire, and then you have 5 variables, okay, for each factor. Yeah, therefore, totally you get 30 variables in your questionnaire. Okay, I mean, ignore about the demographic. Yeah, these are the important metric variables, okay, for you to run the factor analysis. Okay, so this is to explain this point. Okay, of course, you based on the prior, the past study, you have to determine your current research objective. Okay, so if no question now, enough factors to meet a specified percentage of variance here explained. So normally 60% or higher. Okay, we see this. We suppose have this in the output. Yeah. Okay. Okay. So, okay, correct here. Can you see this is 77.7%. It's a cumulative percentage. Okay. So means we consider what is the meaning of 77.7 means if you consider these four factors, the four factors, you already consider the total variation. Okay. So, okay, means you already consider the important factors. Already sufficient. You have to extract the important factors from these many variables. Okay, so this is considered quite good because the guidelines say minimum 60%. Can you see 60%? Okay, actually also discussed a bit just now. Yeah, can you see here? Okay, percentage of variance. Okay, so 77% is considered very good. Okay, yeah. Okay, if no question, now we see next here. So factors shown by scree test, same thing. Yeah, to have a substantial amount of common variance. Yeah, okay. So actually, from the scree, this year we only have the scree plot, not the scree test. Yeah, so we only have the number. We only can find the number of components here from the scree plot. Okay, and therefore it's 4. So this one is more important, yeah, for the to determine how many factors you should have. Means the factors that you have enough or not, yeah, based on the output here. Yeah, 77.7. This is more important. Okay. Yeah.
to ask,
Yeah.
because this one, as you say, we need to have a eigenvalue more than 1. So
Yeah.
can it be the case happening that after they do the calculation, then they list out all the eigenvalue more than 1, but the cumulative is still less than 60%. So in this case, can we add on the component 5 to make it to be more than 60%, but the eigenvalue of others are less than 1?
Okay, good question. This is possible because here means what? Meaning that you cannot determine means what? Means the factors are quite similar. You do have some quite important variables. Okay, so you can do that. Actually, it's not too it's a little bit subjective. But first, let's say you want to add one more, you add the component 5, not component 6 lah, like that. Okay, so to make it become what do you call? Yeah, to make up the 60%. Okay, but actually another method is that you can only choose one criteria. You cannot have two. You can say
So we follow the eigenvalue more than 1.
yes, correct.
So there
Okay.
is a sequence of
Remember just now we can only choose one, cannot choose two. Yeah. Example here, what here? Can I say, if I want to base on the eigenvalue, therefore put here 1. I can also base on the fixed number of factors. Either one, you cannot choose 2. Okay, like that. Okay. Okay. So it means you stick on one criteria, already good enough. Okay, yeah.
those are the ideal criteria. If meet all, then it's like almost perfect. But if not, then
Almost perfect. Okay, of course, another method you can also see the journal see normally what method people use. Okay, but eigenvalue considered quite good already. It's quite good what they call criteria. Okay, for us. Yeah. So continue. Yeah. Well, okay. So continue. Yeah, here. Okay. Yeah. So more factors here when this heterogeneity among the sample subgroups. Okay. So okay. Uh, more factors. Yeah, when there are okay. So but this one you can see in a show yeah later. Okay. So okay. So basically we use the eigenvalue or already good enough lah. Okay, we see. Um, okay, we see next. Yeah. Okay. So we see estimate the factor matrix. Okay, the processes of factor interpretation. Yeah. So we estimate the factor matrix. Okay, so factor matrix means uh, refer to this table. Okay. Again, SPSS they try to use some term that different from others. Otherwise, people say they copy. Therefore, they use component, not factor. But it's the same thing. Okay. So this factor matrix. Okay. So we've seen this a bit just now. Okay. Yeah. So this step 1, we get the component matrix. Okay. And then we do, okay, we see factor rotation. Okay. Factor rotation, we get one more part to discuss, but we see it in the show. Okay, it's okay. We can see it now. Yeah, no problem. Yeah. So I mean the concept later we can see, but we see the rotation now. Okay. Oh no. Okay. Got. Okay. Okay, correct. This one correct. Okay. So you see, just now this is a problem, correct? The problem is on x9. So x9 can belongs to factor 1 or factor 2. Now we see x9 is clearer. Yeah, it's under factor 1. Okay, so meaning that we cannot be so strict on the cutoff point. 0.48 also considered good. Okay, so from here it's easier for us to see the variable belongs to each factor. Example, x5, 2. X7, 1. Yeah. The rest is very small. Okay. So x8, 2. Yeah. x9, 1. Yeah. Okay. x10, 2. Can you see it's very clear? Yeah. Means there must be one number quite big and another quite small. Others quite small. Okay. Okay. 11 also easy, yeah, 4. Yeah, 12, 12 also easy, 4. Yeah, x14, 1. x16, 1. You see, it's very easy. So this one, x17, 3. x18, 3. x19, 3. Okay, see, it's very easy. Okay. Can you see the mention albumin if K Kaiser normalization? Okay, this is a method. Okay. Okay. So we see in the short while what is the location? Either short while or weekend. Yeah, it's okay. We see how. Yeah. Okay. So this is the okay, in SPSS they call it pattern matrix. Okay. Yeah. So this one not easy to see, but this one after rotation very easy. Okay. So this is the here. Okay. Any question, please?
So, sir, in the pattern matrix, we don't need to see whether it's more than 0.6 or 7, just to pick the highest number, right?
Okay, good question. Okay, so we pick the highest number, and also we see the different a bit or different a lot. Example, yeah, let's say, okay, because of course, if in case you want, you will be very strict, you can also remove x9. Remember, x9 because the commonality is quite small. Yeah, below 0. No, sorry, different advertising. Okay, therefore we cannot remove because, yeah, but of course it may remove x8, then the outcome may be different also. Okay, okay. The second thing, we don't have a very strict cutoff point. Yeah, okay. So therefore, actually, 0.488 also can be used, but normally we don't want to see one row they got two very high value. Let's say 0.5, 0.9, 0.8. Okay, therefore the cross ruling is very obvious. Okay. Some textbook even suggest to remove. Okay, to remove the cross ruling, because with the cross ruling, we don't know how to do interpretation. Okay, so therefore, at least now still quite clear 0.488. But if only one variable, meaning that not going to affect the overall result. Therefore, still important, still useful. I mean, the rotation still useful for us.
So, sir, you're saying that if cross-ruling is better to remove totally the variable rather than put them overlapping at there are two factors, right?
Yes, correct. If you remove or put them overlapping, you better remove. Okay, yeah, like that. Okay, of course.
So
Yeah, of course. If possible, we try to do rotation. Like that is better. Even better than what they call, better than we remove it. Yeah. Okay. Yes. Question.
is there any difference for the positive and negative signs in this pattern matrix? Or we
No.
need to choose the positive instead of negative, or they are
No,
the same?
no. Okay. Good question. Good question. Okay. Yeah. So okay. So actually, positive means positive relationship. Negative means negative relationship. Okay. So remember the linear, the correlation. Of course, here refer to the Pearson. Yeah. Okay. It's general idea because either Pearson or Spearman, we still use the same method to do the interpretation. Just like the method on the calculation a bit different. Okay. So Pearson is parametric. Spearman and Kendall are non-parametric. Okay, we see this now. Yeah. Okay. So let's say positive, yeah, means here, yeah. Negative means this area. But we don't care positive, negative, but you want strong. You want strong relationship. Let's say negative 0.89. Yeah, positive 7 positive 0.79 like that. Yeah, this one we don't want. This one means no relationship. Okay. What is the meaning of a positive relationship? Meaning that when, yeah, example, yeah. So when Maybank share increase, yeah, Hong Leong Bank also increase. Both positive. Okay, this is positive. Okay, but negative, this one increase. This one the share price drop. Okay, therefore it's negative. Okay, So here can be another example. Let's say your income and your consumption. Yeah. Okay. Your income increase, you spend more money. Therefore, positive relationship. Okay. So let's say price drop. Yeah. Okay, here. Price drop, you spend more. Okay. Therefore, it's demand theorem. Yeah, it's negative relationship. Like that. Okay. Yeah.
So that means if I have a factor called measuring the employee satisfaction, and inside employee satisfaction, I have a few variables, and inside these few variables, some is positive, some is negative, then it become offset, become no effect already, is it?
Okay, good question. This one may affect you when you do the regression, but for this context, no. Yeah. What you say is correct when you do the summative, summated skill. We see this in the short while, also in this chapter. Yeah. Okay. So let's say you are right. Let's say some example. Yeah. This one is okay. Okay, this one is important also if you want to prepare the questionnaire to do your capstone. Okay. Again, employee what satisfaction? Okay, satisfaction. So let's say okay, equipment. Okay, let's say equipment enough or not for you to do the work, including the internet, including the laptop, and so on and so forth. Okay. Let's say 5 strongly agree. Yeah, means equipment provided is sufficient to perform my work and so on and so forth. Okay. So 5 means strongly agree, 1 means strongly disagree. Okay. Okay. So any question? Negative. Equipment. But anything negative? 5 means strongly agree. Yeah. Okay. Some question. Okay. I can depends on the question actually. Okay. So okay. Let's say working hour. Okay. Working hour is not flexible. You see, depends on how you ask. You say working hour is not flexible enough. Therefore, you also strongly agree. You just strongly agree. Okay. So therefore, they will offset it. Let's say finally, the wait. Okay, it's correct. So because strongly agree for equipment, is strongly agree. Because equipment good, therefore supports more positively affect satisfaction of the employee. But working hour not flexible, what actually negative, yeah, affecting the what they call the satisfaction. Therefore, they will offset. Yeah, you are right. Okay. Therefore, if you want to use questionnaire, you should also you should do it in different way. Okay. Equipment you can means let's say agree means happy. Agree means satisfaction. Yeah. Okay. So let's say working hour, you may change the a bit, or you put it in other variable. Okay. Yeah. Okay.
We need to say same variable. We need to have a same direction instead of
Correct.
got it, sir.
Okay.
Thank you.
Okay.
So can you go back to the statistic SPSS result again? Just want
Yeah.
to confirm something with you. Okay, let's say if I use the factor 1, the component 1, and then some is negative, some is positive. So I only choose positive for the factor 1, or should I include negative also?
No, also include negative. Negative.
Okay.
Okay, include negative. Yeah.
So I got negative obsolete. That one is which one?
Including this, including this.
Right. So everything negative, positive, you just put it.
Yes, correct. Yeah. You want the absolute value. Yeah. Including for this. Okay. Okay. Example. Let's say satisfaction. Yeah, negative 0.863. So the one we also take the negative 0.863. Okay. Yeah. So means we don't want the positive 0.618. We want negative 0.863 because that one is stronger relationship. Yeah, with the factor 3.
So meaning to say if the factor 1 got positive higher and also the other variable is a negative higher, I choose these two, positive and negative together for factor 1, and it will have this effect to net off the submitted.
Again, sorry, again?
I'm trying to understand that if, let's say I have to pick up the factor 1 and I choose the highest one from factor 1, example variable for
No.
x7.
Based on variable.
Yeah,
It
based
is based
on
on
all
variable.
the four factor, and then I choose which one is the highest. If the highest one, I will put under factor 1. And then inside this factor 1, if I see all, some of it is positive, some of it is negative. Will it have this problem of offsetting or the impact? Because some is negative, some is positive, the relationship.
Okay, good question. Okay, but if you use, depends on you. If you use the factor score, it means not going to affect. Yeah. Okay. Okay. We see factors. We already have this factor score. Okay. We already have the factor score here. Yeah, because we save variable just now. You can see here got 4. Okay. Okay. So this is for the what? For the first. Yeah. For the first factor 1, factor 2, factor 3, factor 4. Okay, like that. So means if you use this, means not going to offset. Yeah. Okay. Okay. Okay, we will see it a bit later. But if you do, if you use the, let's say, okay, use another method. Yeah. Example, use the original data. You believe that this one, 5 variable, they can group together, become 1 variable. Use the software to do calculation. Okay. Transform, recruit into different variables. You see, 5 until 9 you sum together, but actually some of them have they may offset to each other. Okay, therefore, and this one you use this method, you recruit into different variable. Alright, 5 until 9. 5 until 9. Sorry, not recruit. Transform, compute variable. Okay, so you x5 until x9 you combine together. Let's say sum. You create a new variable called sum. Yeah. And then x5 plus x6, yeah, plus x7 plus x8 plus x9. Okay, so you get by using this procedure, you will get one variable called sum. Okay, so yeah. Okay, for the rest you listen also, because we are going to see this also in the following slides, either today or tomorrow. Okay.
So I post a screenshot on the chat. You look at the one that I posted in the chat there.
Wait. Okay. So you see, you get a sum. So this one is one variable, but representing 5 columns. Okay, 5 until x9. So by doing so, maybe they will offset to each other, something like that. Okay.
For this case, the factor 4 actually offset, right? Negative in one is negative, one is positive. X11 and X12. So in this case, we can park this under factor 4, or should we split it off?
Okay. Okay, so this pattern, this is the x7, x11, okay, x12. Okay, so factor 4 means factor 4 got few. Okay, actually, not much problem, because here they will do some calculation and then make a new variable for us. Yeah, we call this factor score. Can I say? They will not offset it for us if you use the factor score. Can I say? Yeah. So okay. But of course, the problem is that later may not be easy for you to interpret the coefficient. Okay, later. Okay. So therefore, still better you follow the guideline just now. For each variable, they have same direction. Example, 5 agree. Yeah, 5 agree, 4. Let's say 5 and 4 all will positively affect the dependent variable, like that. If you think negative, you put it in other variable, like that. Okay, this way is better.
Thank you, sir.
Okay,
Got it.
yeah. Okay, so continue. Okay. So this is the factorial rotation. We got many methods to do the factorial rotation. Already discussed. Not say discussed. We just seen the output. We see more detail later. Yeah, I think today, suppose. Okay. Okay. So we see also the factor interpretation. So for factor interpretation, we expect you to do a few things. Okay. So yeah, correct this one. Okay. So first thing, make sure you know factor one. Which factor, which variables belong to factor 1, which variable belongs to factor 2, like that. Okay, that's first thing. Okay, discuss already just now. You can do rotation and use the final result. You have to do the grouping. Okay, means which variable belong to which factor. Okay. So second thing, you should be able to. Of course, I know sometimes maybe not easy, but you can try. So let's say, okay, we can see here. Okay, I think we can see this, discuss it now. Yeah, means give a name. Yeah, give a name to the variables, to the factors. Okay, so here we should have four factors. Yeah, okay. So try to give a name to the factor. Maybe can discuss a bit now. Yeah. Okay. So we see example. Okay. Okay. So we see where. Okay. So let's say here x5 belongs to 2, 1. This 2 here, this one. Okay. But actually it's quite similar, product line. Okay, quite similar also. Yeah. So okay. Okay, and then this one. Okay, this one, and then okay, 618. Okay, okay, okay.
X17 should be between.
Oh, okay, okay. Yeah, thank you, thank you. Where my pen? Why cannot? Oh, where is eraser? It's okay, okay, it's okay. It's okay. Okay, so now we see, let's say component 1. We start with component 1. Yeah, how to, anyone want to give a name? Maybe not too easy, because complaint and also product line come together. Order billing, delivery speed. Is this after sales service? Order billing. Okay. Product line, complaint. Order and billing. Order. Service quality. Anyone? maybe also not too easy. Yeah. Okay.
Maybe customer experience.
Customer experience. But if customer experience, how about number 3? Product is order and billing. Documentation. Product line cannot be complaint. Yeah, the recipe is not document. Okay. So competitive pricing, number 4 maybe easy. Warranty and complaint. Warranty and claims. Competitive pricing. Looks like they compare more to comparison, is it? Okay. Or what? Competitor effect. Okay. So sometimes maybe not too easy. Therefore, you cannot demand too much on this area. But try. You try to give 1 or 2 names. Yeah. Even okay, as I mentioned just now, no, previous class, we have another 2 method to use. Yeah. So first is let's say you cannot give a name to represent 3 factors, but at least you give a name to represent not 2 factors, 2 variables. Okay. Yeah. Okay. So I think X17, 18, I think is easier. Yeah, these 3 are quite similar. Okay. So So for number 2, you can use x5 and also x8, these two, you have to form a name, to find a name. Okay, like that. So that's the first method. Second method, you use the name, it means it's the last option. In case you cannot find a name, you just use the name with the highest correlation. Okay, let's say number 1, just use complaint distribution. Okay. Okay, so we see next. Yeah. Yes.
This matrix as you copy is this is a structural matrix, and the first one we saw for the rotation is a pattern.
Okay. Different. Yeah, I'm sorry.
But it's I mean the selection, I mean it's almost, I think it's the same, but just the numbers are not exactly the same.
Okay. So, but you still follow the guideline I mentioned just now. If possible, you find a name that represents all the variables. Okay. In case not, you at least representing 2 or 3 variables. Lastly, in case still cannot, you find you use the name that with the highest correlation. Yeah, highest factor loading. Yeah, that's it. Okay. Okay, we come back here. Yeah. Okay. So that's the factor interpretation. Okay. So now re-specification of the factor model if needed. Yeah. So example for your capstone, you may consider to remove the commodality that below 0.6 as what we discussed just now. Okay. Okay, so this is advertising is below 0.6, may consider to remove. Okay, then you run again. Okay, so okay, but again, assignment and in-class exercise not that strict compared to your capstone. Okay, so we see. Okay, so of course I will show you either today or next class how to use the different rotational approach. Yeah, you got 2 category. Yeah, each category got few method. Okay. So you need to extract a different number of factors. So okay, I can show you now. Yeah, you can do it now. It's okay. So means I still keep the, but it's okay. I think it's okay that I do it. Yeah. So means we keep this one, but we can do one more testing now. Up to you. You can follow, but it's like this. Based on this output, we have 4 components. But now we try to do 1 more, 2 more. The first one is 3 factor, and another one 5 factor. Yeah, therefore, and then we can do some comparison. Okay. Okay. So let's say here, okay. Now I put here 3. Means that inform the software. I want only 3 factors. Don't want more, don't want less. Okay. Okay. Then you see you compare the result. Yeah. Okay. Okay. So therefore, they only give us 3. You see here, eigenvalue even 1.0, but they did not consider. Yeah, because we already instructed the software. It give us only 3 factors. Okay. Okay. You can see here only 3 factors. Okay. Yeah. So you see the pattern matrix. Okay. So okay, I think it looks quite similar. The product line still quite similar. 0.5 and also also negative 0.497, quite similar. This only one. This one only one. This is quite small, a bit small value, below 0.5. Okay. So as I mentioned, use absolute value, but it's still below 0.5. Yeah. Okay. So this is quite obvious. It's quite high, negative 0.6. Yeah. Okay, like this one. So we can do again and then ask the software to give us 5 factors. Do some comparison. Okay. Yeah. Okay. So next we have another option to use different rotation approach. Yeah. Okay. Okay. Here, you can see we can change the method of extraction. Okay, or yeah, this one discussed already. Sorry, this one done already just now. Okay, so we can also use different method of extraction. Yeah, but now this module we only discuss one method. Okay, the principal component analysis. Okay. Okay. So means you may explore yeah another different method if you want later. Yes, question.
The pattern or structure metric. Just now you refer to pattern. Actually, what's the difference pattern and structure metric? I mean the diagram.
Okay, thank you. What is the difference between the structure and also the pattern? Okay. No,
This one and the
Oh, okay. Okay, wait. Okay. Wait. Actually, quite similar. Is it the result is quite similar? Okay. Okay. So actually, both also for Kaiser. Yeah. So actually, for us, we want to use structure. Yeah, not the pattern. Okay. Structure, not the pattern. Okay. Okay. Yeah. So the beginning one actually is the component. Yeah. So we should use the structure. Yeah. After rotation. Okay. Okay.
So, sir, last in the first few slide of this factor analysis, when you see the first this correlation matrix, so for this matrix as you see in the structure, is that the Pearson coefficient or it's not the same?
You mean here?
Yeah. I mean, this one is almost the same as what you saw just now, right? It's also a rotation.
No, different thing. This is only Pearson. This is only Pearson. Yeah.
Okay.
They don't yet consider the factor, but it's some guideline for us. Can I see? So that you know the idea, roughly the idea. Yeah. But we actually want to see the correlation, the factor loading. Factor loading is the relationship between the variable and also the factor. Okay. Yeah.
Okay, not the same. Okay.
The same. Yeah. So continue. Yeah. Okay. So we see, yeah, okay, we can see now factor rotation of the factors. Yeah, now, yeah. Okay. So sometimes, yeah, sometimes the original, the initial solution may not be so good. Yeah. So example. Okay, now we want to see the initial one. Means the data driven. They give us four. Yes, correct. Can you see? Yeah. So the component matrix they give us four. Yeah. Four components. Yeah. But maybe got more what they call more cross loading. Yeah. Okay. Means we don't know the variable belongs to which factor. Okay. So therefore we can do rotation. Yeah. To find therefore rotation means make our life easy to know to classify. Yeah. To know which variable belongs to which factor like that. Okay. So we see what is rotation now. Okay. So it's the different axis of the factor are turned, yeah, about the origin until some other position has been reached. Okay, we see this now. Okay. Yeah. Okay. Don't worry, later we'll come back. Yeah, we see this one. Yeah. It's okay. We got two rotational approach. Okay, orthogonal and also oblique. This one is the one that we use here in the SPSS just now. Okay. So remember, obedient is similar obimin, yeah. Okay. So means is what is the meaning? Meaning that no they have relationship. Okay. Okay. They have relationship between the x and y. Here means this one means no relationship. Yeah. Okay. Okay. So the axis are maintained at 90 degree. Yeah, 90 degree means, of course, you know lah. Yeah, means like this. But after do rotation, but they still keep the 90 degree. Means what? Means even do a bit rotation, can you see? They turn to right. Yeah, the whole diagram turn to right a bit, but they still maintain the 90 degree. Can you see? Y, X. Yeah, this is Y, this is X. They maintaining the 90 degree. Okay. But ubiquitous, no. Yeah. So original like this. Yeah. But they turn it, they may not maintain 90 degree. Normally, they did not maintain. So example, maybe like this. Okay, just 60 degree. Yeah, but here is Y, here is X, like that. Okay, this is the difference. Okay, therefore axis are not maintained at 90 degree. But don't worry, not going to ask you to do the diagram, but just see the idea. Yeah, in the testing, the test or assignment or test, assignment no. Yeah, assignment maybe. Okay, factor analysis also included in the assignment. So basically, ask you to do the get the output and then do some discussion. Okay. Okay, so if no question, we see like this. Yeah. Okay. So here we see got two factors. Yeah. Factor 1, factor 2. Therefore, it's like x and y. Okay. So the original position is like this. Can you see? This is original. Yeah. Okay. And then these are data, the variable. Variable 1, variable 2. Yeah. 3 and 4. Okay. Okay. So using the original data point and also the axis, it's not easy to do the grouping. Yeah. Okay. Not easy to find the relationship. Therefore, is it x1, x2? Okay. It's not easy for you to see x1, v1, v2 belong to 1 or 2. Not easy because it's in the middle. Can you see almost middle? Okay. Okay, so 3, 4, 5 also not easy. Maybe you can say 3, 4 is 1. Yeah, x5 not easy. It's in the middle. It's like the cross ruling. Can be under factor 1, can be under factor 2. Factor 2 is y. Factor 1 is horizontal. Yeah. Therefore, we do some rotation. You turn to right a bit. Turn to right, but maintain the 90 degree. Therefore, now v1, v2 is quite close to factor 2. Can you see rotated is new, rotated, and then 3, 4, 5. These all three belongs to factor 1. This is the logic.
So may I know what is the reason we want to do the rotated?
Yeah, we discussed a bit just now. Means we want to know better how to do the classification. Which variable belongs to which factor.
Okay, got it, sir. Thank you.
Purpose. Okay, this is purpose. So you see, 3, 4 still easy, but the V1, V2, and V5 are not easy for us to decide. They should belong to each factor. Therefore, we do rotation. Yeah.
Sir, if we have 4 factors or 4 components, so how they choose which 2 factors should be rotated first?
Okay. Let's say again, you say got 4 factors.
Yeah, just like our example, like 4 factors. Then which should be the first 2 factors to be doing this rotation first, or?
Okay. So in general, okay, in general. So what they do, they will do the see the beginning. Yeah. See the beginning, the initial output. Okay. So the idea is that they try to distribute the variance. They try to distribute the effect to the next. Okay. So example okay. Okay. So let's say for which one? Okay. So x9, x9. So therefore, they try to distribute to the next. Yeah, maybe 3 or 4 or like that. Okay. Okay. But actually not much important for us. Okay, they will do the work for us. Okay. Okay. Yeah. So we see next. Yeah. Okay. Now we are here. Okay. So since unrotated factor solution extract factors based on how much variance they account for. Okay. So with each subsequent factors accounting for less variance. So therefore, they will distribute to the next variable. Okay. So you can see the ultimate effect of the rotating actually is that they redistribute the variance. Yeah, the effect. Yeah, from the earlier to the later one to achieve a simpler, theoretically more meaningful filter pattern. Yeah. So I think the formula may be too advanced from us. Okay. So you just know the idea and you make sure you know how to do. Okay. Okay. So we see. Next, yeah. Okay. So what is the difference between the pattern and also the structure matrix? Yeah. So should be the working. So okay. So for us, we see the final one. Yeah, already good enough. Okay. So we see only these are the structure matrix. Okay. Okay. So we see. Yeah. Okay.
So the rotation part is decided by the software, or we need to put certain degree to rotate?
No. No need to put the degree. Yeah, no need. Yeah. We just choose the method.
Okay. Thank you,
Yeah.
sir.
Okay. Now we see. Wait. I think got one more question. Is it? For price of product, I don't understand. Hello. For price of product, I don't understand. Okay, you explain a bit more. Can get yeah.
Just now the classification, the names. You want to rename component.
Okay. The price of the product. Okay. Maybe not too good. Kind of. Maybe not too good because got two. Is it? One is the price and the one is the.
Billing.
Got two. Is it? Oh, okay. For naming of the. Yeah. Warranty. Yeah. Okay. So got two. Competitive pricing and also one more is the warranty. Okay, pricing warranty. Yeah, not easy also. Okay, but again, worst comes to worst, you just choose the one with the higher higher factor loading. Okay, yeah. Okay, ask now. Yeah.
So for the rotation, so just now the example shown is a 90 degree, which is orthogonal. Yeah, but in the example shown just now, in the rotation part, the windows of a rotation, we chose a direct oblique. So
Yeah.
this direct oblique is, I thought it's as I say, it should be the oblique one, not the orthogonal, or
Oh, the one is under the one we use in the output actually is this one number 2.
no, it's
Yeah.
not 90 degree.
Yeah. Sorry? No, because they are not 90 degree. 90 degree means they are not they have some relationship between the factor 1 and factor 2. Okay, not?
You mean the variables are not exactly on the axis, right?
Not the variable. The variable is the point. The one on axis is the factor.
Because on the next slide, you're showing that the axis are rotated just 90 degree. So yeah, the oblique, just the oblique one.
You mean?
Yeah, this one now, the oblique one, then this one, see
No,
the
this is not 90 degree. This is not 90 degree.
yeah, not 90 degree.
Yeah. Before it's not 90 degree. Can you see? Yeah, like this. Correct.
So that means the axis will tend to be closer to the variables. So that's why it's not 90 degree.
No. Meaning that they try to find the solution, but they a bit more flexible. You can think this way. They are more flexible. Therefore, they yeah. Okay.
Okay, so in our SPSS, we always use the oblique one, not the orthogonal, right?
Okay, actually good question. So you can use any. Yeah, it's not fixed. So any rotation method they can give you good output. Therefore, it's flexible. Okay.
Okay,
Can
but
you see here? Wait. Can you see here? Yeah. So it may also use a different rotation approach, but for you to get a new good output, because all methods are good, you can use. I mean the rotation method, all good, you can use.
but in this rotation window, if I put in the chat,
Not yet. Okay.
which one is the orthogonal?
The rest. Okay. Yeah. So
The rest are all orthogonal.
the first worry max, query text, and also equal max. Okay, but pro max I'm not sure. I need to check later. But the first three confirm is the first three are query max, worry max, and also equal max actually belong to orthogonal. Okay. Yeah, in the slide already in the slide. Yeah. Yes, correct. Okay.
Okay.
So sorry, the direct oblique mean that's the delta equal to 0 means what does it mean?
No, it's okay. Just use the default. Yeah, it's okay.
Thank
Not
you,
so
sir.
important. Yeah. Okay. Okay. Now, if no question, now we continue. Yeah. Okay. So we are. Okay. So this one done. This one done. This one done. So this one done. Okay. Therefore, again, the orthogonal means not too flexible, and then they assume that factor 1, factor 2 are independent. There's no relationship. Okay. So, okay. So you see, using of course for this data, for this example, either method you use, you can come up with the same result. Means x1, the v1, v2 belongs to factor 2. Yeah, 3, 4, 5 belongs to the factor 2. Okay, yeah. No, sorry. Sorry. V1, V2 belongs to factor 2, and then V3, 4, 5 belong to factor 1. Yeah, because we rotate this way. Yeah, turn to right. Turn to right. Okay. So the dotted line means orthogonal. Yeah. The solid line means representing the oblique. Okay. Rotation. So for this case, different not much. Means either method you use, the V1, V2 still belongs to factor 2. Yeah. V3, V4, V5 still belongs to factor 1. Okay. So but again, different data, different outcome, different output. Okay. Okay, so if no question, we see next. Okay. I mentioned just now, for these three all belongs to the orthogonal, okay, orthogonal rotation method, okay. So when you are free, you can test here one by one, okay. Okay. So of course, this not too. It's okay. You can see a bit. Yeah. Actually, this is based on this one. You see, oblique is more practical. Okay, you see a bit more. Yeah. So orthogonal rotation is most widely used rotational method. Okay. So okay. In fact, if you see the older version of the SPSS, they don't have the oblique mean. Yeah. Okay. They don't have the oblique mean method. Okay. So version 28 they have. The old one, let's say 26 they don't have. 26 still new but not too new. Okay. Okay. So these are the preferred method when the research goal is data reduction. Therefore, is the factor analysis. So we reduce the data. Yeah. Okay. Or either you want to find a smaller number of variables. Yeah. So if from 30 you reduce to 10, you have 10 variables or 10 factors. Okay. Or a set of uncorrelated measure or subsequent use in other multivariate technique. Okay, we see this part meaning that we can already discussed. Also, we can get the factor score here. Can you see 4 factor, and then each factor we got their values. Okay, so factor score for the first factor, second factor, third and fourth. And then let's say if you want, you can also use these four columns to do further data analysis. Example, maybe in the multiple linear regression, like that. Okay. Okay. So this is the how you can link factor analysis with other method. Okay. Of course, you can also use it in the structural equation modeling or maybe the logistic regression, like that. Okay. Okay. So we just copy the data to another file. Okay. Okay. Now we see oblique rotation is more practical. Okay. So best fitted to the goal of obtaining several theoretically meaningful factors or construct, because realistically very few construct in the real world are uncorrelated. Okay, so suppose they have some relationship. Okay, I mean the constructs. Okay. Okay, so of course this one based on some theory. It means you can support by the past journal or some theory. Okay. Wow. Okay, if no question, wait. Okay. Okay. No, actually it's okay. Yeah. Because actually in general all are good. Okay, all are good. Yeah. Okay, so continue. Yeah. As long as your output is good, means you can easily do the classification to know the variable suppose belongs to each factor. That's the most important thing. Okay. Okay. Now we see which factor loadings are significant. Yeah, we got few factors here to consider. Okay, so we see this now. Yeah, so practical significant. Yeah, okay, this one discussed a bit just now. So minimum 0.5, but here practical significant based on the guideline is 0.3 or 0.4. Means 0.3 also consider good. Okay, so this is the factor loading. Okay, so therefore for us actually all quite high already. Yeah, so based on the result just now. Yeah. Okay, so structural matrix, can you see? Okay, so just now the minimum was 0.488. Okay, 0.89 and then 0.6 something, 9, 0.6. This one 8, 9. They're all quite high. 6. Okay, so 8 and 8. Okay, quite high. Okay, so because we already we filter 3. In 3 variables. Okay. So continue. Yeah. Okay. So actually 0.3, 0.5 is minimum. Yeah. More than 0.5 is for the practical significance. Okay. So this is the guideline that we can use. Okay. Another one is that we also consider the sample size. That means not only see the value, we also see the sample size. Okay. So if you want, you can also find this table from the textbook. Yeah, Hey 7 edition. This table is from this textbook. Okay. So you see guideline for identifying the significant factor loadings based on the sample size. Okay. So means with the condition, the significance is based on the 5% significant level. See the alpha. See the bottom 2 lines. Okay. So alpha 5%, and then the power is 80%, means it's 0.8. Remember power we discussed in chapter 1. Okay. So power is 0.8. Okay. And then the standard error is shown to be twice. They are those of conventional correlation coefficient. Standard error higher, therefore more difficult for us to reject the null hypothesis. Therefore, this is quite conservative. Okay, means they construct this method so that not easy for us to reject the null hypothesis. Therefore, it's a bit more conservative. Okay. Okay, we see how to use this. Example here, let's say fatal ruling 0.6 is considered more than 0.6 considered good for if your sample size is 85. Or let's say you want to consider significant, your sample size must be 85 and above. Okay, so therefore, if you want 0.3 also significant, you must have 350 observation in your sample. Okay, therefore, in conclusion, sample size higher, the requirement for the fatal loading, is lower. 0.3 also considered significant if your sample size is 350.
So can you show us how to get the factor loading in SPSS?
No, we have already. We have already. Okay, this all fatal loading. 0.159, 0.868, all these are fatal loading.
Oh, okay, got it.
Okay.
Thank you, sir.
Yeah. Okay, if no other question, we continue. Yeah. So, yeah. So this second guideline means we also see the sample size, right? So and then and also the statistical significance, alpha. Alpha is 5% for this table. Okay. Okay. So if no question, now we see next. Okay. So we see next is the number of factor. Yeah. Okay. So number of factor, let's say more. Yeah. Number of factor more. Therefore, the in general, okay. So in general, number of factor more. Therefore, the loading also should be high. Yeah, the factor loading. Yeah. Okay. So example, let's say your factor got 4. Yeah. The factor loading 0.5 also good. But let's say you got 6. The fatal loading should increase, maybe 0.65, like that. Okay, so 0.65 only consider significant. Okay, so these are some guidelines. Means what? Means you should not simply increase the factor. Because increase factor, they will share the loading with among many factors. Okay, actually, therefore, it's not too good. So try to keep it maybe 4 or 5 like that. Okay, depends on your number of variables. Okay. Okay, but variable can increase. Okay, can be more. Okay, so variable increase, the factor loading actually drop. Okay, so can see here is more, but here is less. Okay, so example, let's say you have 30 variables. Okay, the loading can be 0.5. Okay, but let's say you increase to 40. You have 40 variables, because let's say you got 40 variables, means you have more information. Okay, for the software you have to analyze. Okay, so therefore, let's say 40 means 0.4 also consider significant.
Example, if my sample data set has like 80,000, so meaning the loading 0 around this can
Yeah. 0.3 or 0.2 also good. Yeah, okay. So we see the guideline just now. Yeah. So 350. Yeah. Okay. Okay. Because your sample size increase, you have more information for the software you have to analyze. Okay. So this
I got share something in the chat there. Can you
okay.
can I ask you one question regarding this one?
Yeah, sure.
Let's say S12 is the loading factor loading is negative 0.420, and we only have 100 sample size, and this one is the highest one. So are we going to drop it, or are we going to include in the factor 3?
Okay, we see this now 0.4. Okay, so yeah, the sample size is 100. Okay, 100 100 and then 4.2. Okay, good question. We see this now. Yeah. So 4.2, therefore not enough. Can I see? 4.2 is in between here. Yeah, in between here, no 0.42, 0.42. Yeah. Therefore, the sample size should be about 770, about that, in between here. But 100 not enough. It's not enough information for the software. Yeah, not significant, correct? Not significant. Okay. So
we should exclude it from our factor 3.
Good question. Okay, I see again. Okay. Yes, correct. So means we should actually remove this. Okay. So we see which one is smallest. Smallest factor loading. Is this 0.42? Any others? Because we should remove the smallest first. Okay, we confirm this now. Yeah. So you are right. Negative 0.42 is smallest. Therefore, we can actually remove this first. Then do it again, testing. Okay. 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 So if no question, now we see next. Okay. This one done. This one done. So now we are here. Okay. So okay, I discussed a bit just now. 0.3 is minimum. Yeah, minimally acceptable. Yeah. So values greater than 0.5 consider necessary. Yeah, for the practical significance. Okay. So means still acceptable, but practical significance should be more than 0.5. Again, you got many criteria. Yeah, if you want to use it in your capstone, you must do citation. Okay. Okay, so continue. Yeah. So a smaller loading is needed given either a larger sample size or more variables. Okay, so therefore when you have larger sample size and also larger number of variables, therefore you need only smaller loading. Okay, also enough. Okay. Okay, so we see. Okay, a larger loading is needed given a factor solution. Yeah, with larger number of factors. Correct. Okay, therefore, you want more factor. Remember, you can instruct the software. You want more factor. Let's say 10, but you need more higher loading. Yeah, to make sure that it's significant. Means you want significant, you must use the higher loading. Okay, from the output. Okay. So we see just now, this is very conservative. They even increase the standard error twice. Okay, double. Yeah. Okay, twice those of the conventional conventional correlation coefficient. Okay. Okay. So therefore, can be considered only as starting point needed for including a variable for further consideration. Yeah. So this point means what? Means don't follow 100%. Yeah. But for academic, we actually should follow. You follow first. Okay, then see how. Yeah. This one maybe next. It's okay. Maybe next class. Okay. So okay. So means okay. Again, you keep the what yeah? Saturday 10 yeah. Okay. 10 yeah. So anyone, I mean, you still can come to APU, but try don't use Bukit Jalil. You know, right? Saturday. There's a game going on. Yeah. Saturday. Concert also. Okay. So means you can come here, but don't use Bukit Jalil. Don't use that route. Yeah, Bukit Jalil Stadium. Yeah. Okay. Other route, okay, no problem. APU not affected. Only that area. Okay.
From the entrance.
Yes, correct. Yes, correct. Yeah, use the near to Standard Chartered Bank. Yeah. Okay. Okay. So today we still keep the variable, the three variable that we don't want. Therefore, we are going to test again on Saturday. Okay. So now we finish. Yeah. Okay. But confirm Saturday you can finish. Yeah, at least one chapter. I mean factor analysis in one chapter. Yeah, at least. Okay. So we can more than 10 hours. Okay. Okay. So any question now? Yeah. Wait. Okay, yeah, done already. Yeah, okay, already discussed. Okay, okay. So any question? Yes. Assignment? Okay. Yeah, quite a lot lah. I think about 10 students. Yeah, given me the data for checking. Yeah. So some data okay, some not okay. Yeah. Okay. I try my best to reply within 48 hours. Okay. If 48 after 48 hours I didn't reply, you will remind me. Okay. 48 hours I reply your message. Are your data good or not good to proceed? Like that. Okay. Okay. Where? Yeah. Okay. If no attendance problem, yeah. Thank you and see you. Okay. I'm at attendance now. Yeah. Okay. Okay, last call. Any more attendance? Okay, no. If no, thank you and see you. Yeah, thank you.
Okay, sir.
Wait.